Hi, welcome to another video discussion for college physics. We're in chapter 4 talking about Newton's laws. We've introduced Newton's first and second law of motion, and now we're going to introduce Newton's third law of motion. That is, for every action there's an equal and opposite reaction, which means that for every force there's an equal and opposite force. So that's a good thing if you're driving a car. If you want to drive a car, your engine will cause your tires to exert a force on the road, and the road goes ahead and has an equal and opposite reaction. In other words, it exerts an equal and opposite force on your car that moves you down the road. And if you didn't believe this was true, just take this car out to an ice rink and slick up the tires a bit and step on the gas, and you'll see he slips and slides a lot. Won't want to accelerate because he can't get no traction. Like that traction is the reaction force of the road. Now, there can be some confusion that comes up, and I was confused when I first learned this, trying to apply Newton's third law along with Newton's second law to figure out how something was going to accelerate. So for example, if you want to know how something accelerates, you can use Newton's second law, F equals ma. That's Newton's second law. That's always true. So if you find the net force on an object, F, and you know the object's mass, then you can directly calculate the acceleration. The acceleration would actually just solve for it. Force over mass. Now, to go about calculating what the acceleration of an object is due to the forces that are acting on it, it's often a good idea to draw a free body diagram. That really helps you identify all the forces that are acting on an object. So if we look at a free body diagram for the car, let's say, and let's not worry about the up and down forces like I could do. Well, I'll just draw them for a second. So there'd be the weight of the car and the normal force on the car. That's from the road. But let me not worry about the up and down forces. These two are knocking each other out. So the normal force is equal to the weight. So if I add them together, I'll get 0. I would get n minus w if I can consider the positive direction up. And since the car is not moving up or down, I know that those two are equal. Otherwise, it's either accelerating up or down, and it's not. So let's just consider the horizontal forces, because that's the only thing that's going to make the car accelerate in this case is horizontal forces, because it's just going to stay on the road. It's going to accelerate horizontally. So what can make the car accelerate? Well, it could be the force of the road on the car, okay? The reaction force of the road on the car. And what other forces are involved here? If I throw in this force, let's say I draw this force on the free body diagram. That's the force of the car on the road. Force of the car on the road. And now I know that these are action-reaction forces, equal and opposite forces from an action-reaction force pair. If I go ahead and could take this to be the free body diagram, which is incorrectly drawn, by the way, but let's just say I did it like this, what would I get when I sum these forces? I would get F sub r minus Fc, and since they're equal and opposite, and this actually, I'm taking the left to be the minus direction, so that accounts for the vector, and I know that's going to be equal to 0. And anyway, this is just going to say Fr is equal to Fc. Just move Fc to the right side of the equation, and you have that there, which is just Newton's third law. But it's incorrectly applied here. Why is that? Because I didn't draw a correct free body diagram. So why is the free body diagram incorrect? Because the free body diagram draws the body and draws the forces that are acting on that body. So you isolate the body that you want to understand the acceleration of, that you want to calculate the acceleration for. In that case, it's just a car, so I need to isolate the car all by itself. And I represent that isolated car as this dot that's here all by itself. And now onto that dot, I put all the forces that are acting on the car. And all the forces that are acting on the car, and here just horizontally, it's the only active direction we're interested in, is the force of the road. That's the only force acting on the car. The net force, F, is the sum of all forces, but in this case, it's just that force. And that gives us the ma. So now we could come over here and calculate the acceleration, assuming we knew the force and the mass of the car. So that's an important point. For Newton's third law, there's always an actor and a reactor. So there's an action and a reaction. Action on an object by another object. So where's the other force going here? The force of the car on the road. Here's action, tire pushes on road. What's that doing? That's actually exerting a force on the earth. And if that force is unbalanced, the earth would have to accelerate. But like we're about to show down the line here in another slide or two, the earth is so massive, so this same force that accelerates the car would also be applied to the earth. But since the earth is so massive, 6 times 10 to the 24 kilograms, the acceleration is virtually zero. So that's why you don't notice the earth accelerating the other way when it's pushing you down the road. Okay, now let's go on and define Newton's third law a little more technically, a little more carefully, as we continue to unpack Newton's third. So here's Newton's third law of motion, kind of restated, again, slightly different restatement, but of course the information of the law, the meaning of the law is the same no matter how you state it. And so here we're saying, okay, so for every force, an equal and opposite force. So for there to be Newton's third law, action-reaction, to happen, there has to be two objects. There has to be force pairs, and you have to have an actor and an actee, if you will. So two objects have to be involved. Let's say, I'll say this is object 1, and this is object 2. We've got to have two objects involved, object 1 and object 2. Now, we're going to consider Newton's third law. Let's suppose object 2 exerts a force on object 1. So the force on object 1 by 2 is equal and opposite to the force on 2 by 1. So let's say 2 exerts a force on 1. Let's say 2 attracts 1. 2 attracts 1. So what will this be? This will be force 1 on 2. And Newton's third law tells us there's an equal and opposite force. Take this same force as a vector, put a minus to it, that just turns it the other way. Minus a vector is the same vector but just turned around. So that means if 2 attracts 1, 1 attracts 2 with an equal and opposite force. And that will happen every time. And it could have gone the other way. In other words, they could have been repulsive forces. So I could have an object 1 and 2 again. And when I want to consider the Newton's third law force pairs, what I'll typically do is draw a line between the objects, because the forces always, since it's equal and opposite, it'll end up always acting along the line between them. Usually, I mean, there's magnetism, which can get a little tricky, but we're not going to worry about anything like that. For us, the force always acts along the line between the objects. Strong form of Newton's third law. So if it's repulsive, let's say 2 is repulsed by 1, 2 gets repulsed by 1, then 1 gets repulsed by 2. Equal and opposite. So again, this would be the force on 1 by 2, force on 2 by 1. And that's 1 and 2, object 1 and 2. Okay, and this happens every time Newton's third law, any action-reaction. It always happens, it never not happens. There's always an actor and an actee involved. So when you have a Newton's third law force pair going on, there's always going to be two objects involved with that, or the actor and the actee. Another way to think about that would be to think of a case that might look like it's a Newton's third law force pair, but not a Newton's third law force pair. That could be a case of something like this. Let's look at a box just sitting on the ground. And just consider here, what are the forces acting on this box? Here I have a box sitting on the ground, so the implication is the box isn't moving, it's just sitting there on the ground. But there are forces on it. There is the force of gravity, so there's the weight force on the box, which as we know is equal to its mass times gravity. Now, if that were the only force acting on this box would be moving. It would be in free fall, actually falling. But since it's not falling, we can see it's just sitting there on the ground. That means there has to be another force acting on this box. And it's true, the other force is the support force, known as the normal force. We call it the normal because it's perpendicular. It's perpendicular to the surface that's exerting the force on it. Here, the ground is the surface. So we look at this situation and go, okay, this is a clear example of Newton's third law force pair. Huh? Is it? Well, I just got finished saying that there always needs to be an actor and a reactor. Here, what's the actor and the reactor? Is this Newton's third law force pair? Well, okay, Newton's third law force pair. No, it's not, because all these forces are just the forces acting on the one box. So for example, if I draw a free body diagram for the box, what do I have? I'll have its weight going down, mg, and its normal force going up. And I can see, since it's not accelerating, it's just sitting on the ground, what this will tell me is that the normal is equal and opposite. That's true, it's equal and opposite to the weight, and it'll tell me, okay, the normal is equal to the weight. But confusingly, that's not a Newton's law force pair. Okay, so what's the Newton's law force pair? What's the action-reaction force pairs in this situation? What's the other object in this situation? Well, it's the Earth. That is the case. So the Earth is involved here. So if I wanted to see what's going on here with the Earth, so if I look here, let's see if we do a free body diagram of the Earth, what do we get? What does the Earth get? It goes, okay, the box is pulling up to me with its weight, so the Earth feels that, and there's a normal force from the box on the Earth. That box is actually pushing on the Earth with a normal force. So here's the equal and opposite force pairs. That one to that one, and that one to that one. Those are our Newton's third law force pairs. Here we're coming up to just to wrap up our discussion of Newton's third law. Consider this briefcase this person's holding. So this one's showing all the action-reaction force pairs. So here the hand holds up the briefcase, F1. The reaction force is the force on the hand by the briefcase, minus F1, down. Here there's one object, the hand, and another object, the briefcase. So you have two objects involved in the action-reaction force pair. And here, okay, so what's this F2 on the briefcase going down? What's that got to be? That's got to be the weight of the briefcase. And interestingly, what does the Earth field do to that? From Newton's third law, we know that the Earth feels an equal and opposite force. So if the briefcase is attracted downward towards the Earth is attracted upward towards the briefcase. And that can give us a hint as to what's happening over here. So they're going, in B, is there an action-reaction force pair involved there? Yes, there is. The hand drops the briefcase starts falling down. We could look at the briefcase. So I'll draw a free body diagram of the briefcase right here. Well, let's just do it in place on the briefcase. I'll just draw right there. Okay, what's the force on it? It's just its weight going down. mg going down. And that's equal to ma. And that's why we have a is equal to g. The acceleration, because the masses will cancel. Mass is the same on both sides. Briefcase just accelerates down at the acceleration due to gravity, constant acceleration due to gravity, 9.8 meters per second squared near the surface of the Earth. Now what's the situation for the Earth? Is there a action-reaction force pair here? Yes, there is. I'll draw one for the Earth. Okay, so the Earth is also feeling an action-reaction force pair going up like that. So now the red arrow completes the action-reaction force pair. The briefcase feels a weight force, an attraction due to gravity by the Earth. An equal and opposite reaction is that the Earth feels an attraction to the briefcase going up. This one's down, this one's up, equal and opposite. So now what will happen? The Earth will accelerate up to meet the briefcase, right? Because there's an unopposed force there. So what is this going to mean? So this is going to mean the force on the Earth, and it's equal and opposite, right? So it's mg. This is the force that was on both of these guys. Force is the weight force. Probably should have called it W. Weight force, mg. That's equal to the force on the Earth. And so what does the Earth do? It responds by accelerating up. So how will that work? And what will the acceleration be? This is the force on the Earth, the weight force. That weight force on the Earth is equal to the mass of the Earth, I'll call it big M, times the acceleration of the Earth. I'll just call it A. Like we saw over here, this is also equal to the little mg, the mass of the briefcase, times gravity. So let's look now at what the acceleration of the Earth will be. The acceleration of the Earth, if we solve for it, will be the mass of the briefcase divided by the mass of the Earth times acceleration due to gravity, 9.8. Now let's consider the ratio of the mass of the briefcase divided by the mass of the Earth. I don't know what this briefcase weighs. Let's say it weighs a kilogram, or 10 kilograms even. It's a super dang, he's got it filled with gold bullion and it's heavy. Doesn't matter. The mass of the Earth is so massive. In fact, in this picture right here, everything might as well be the Earth, because it's all part of the Earth, connected to the Earth in a real sense. And the mass of the Earth, anyway, quantitatively is like 6 times 10 to the 24 kilograms. So this acceleration will, for all practical purposes, be 0. It'll be a number that's so small, because the mass of the briefcase divided by the mass of the Earth is a number that's so small, and when you multiply it times gravity here, you're going to get something on the order of 0 meters per second squared as your acceleration. That's why you don't notice the Earth accelerating up to meet you when you jump up and down, or when you drop a briefcase, or when you jump off a ladder or something like that. So next we should get ready to work on doing some example problems where we combine Newton's 3 laws, 1, 2, and 3, all together like a well-oiled machine to solve interesting physics problems.